wanted to just make one quick note here as to some of the issues that we were having last time when we wired up our inverter. So the problem came down to that I had read the data sheet wrong for the PMOS transistors and had pins 1 and 3 reversed. Okay. Once you guys switched those, everything worked fine for the inverter circuit, right? And hopefully also for the NAND circuit. Yeah? Okay. The other thing is the initial assignment had some wires here on the NMOS side, and I, of course, then got those screwed up too. So this is the corrected breadboard picture, right? And what should we have looking at the diagram on the NMOS side? One of the NMOS's pin 1 should go to ground, right? The other pin 1 should connect to pin 3 of the ground to transistor, okay? And then the other pin 3 to output. So let's just double check that I've got it correct this time. So this transistor, I have its pin 1 to ground, its pin 3 to pin 1 of the other transistor, and then that transistor's pin 3 coming over to the output. This is why you guys were backwards yesterday, and that was my fault, not y'all's, okay? Because the schematic was correct, but the breadboard diagram I had backwards, okay? So I didn't realize it until yesterday afternoon that it was your incompetent professor made the mistake, not you guys, okay? Okay, now, was there any reason in particular that I made this NMOS the one that connected to ground as opposed to the other one? No, not really. The reason I picked this one in the diagram was just because it made it easier to get the wires in without them being all messy. But yeah, so whenever you're in doubt, always double check it against the circuit diagram because hopefully that one's not screwed up. Okay. Okay. So does that make sense? Yeah. We. Hmm? You have questions? Hopefully I have answers like Radio Shack. Yeah.
So on the breadboard,
Hmm.
the green and yellow for the second pair,
Hmm. Oh, yep. That should be down one. Okay. Yep. That's my screw up too. So I'll fix that diagram. Okay. So you guys see the issue right here? Where should this yellow one be? Down one. Okay. And why? Well, we need one of each of the transistors controlled by each of the two inputs. Okay. And the reason I color coded them was to try and make it obvious who was coming from where. And it looks like I just was off by a pin there in the picture. So this yellow one should be down one. Okay. So make sense? All right. They'll hire just anybody to teach here. And then they charge you guys like $80 billion in tuition and, you know, feed you sparks and, uh, huh? Yeah. So, one of these days it'd be kind of funny if like Sparks did like a retro themed dinner and served like hardtack and hellfire stew and, like, yeah, like Civil War era foods or whatever, just to kind of see how you guys would deal with it. Right. Yeah. Yes, I'm not a fan of it. Mm. Yeah, I've never been a fan of polenta or grits for that matter, even though I'm from Tejas. So, although I do have to give them some credit. The chana masala yesterday at lunch, that was actually pretty good. So, um, yeah. Okay. Anyway, back to math. So, yeah. So, what I want to talk about today is kind of the logic behind why this is the diagram for a NAND gate, right? It is, and we saw that it worked, and we kind of thought through it on an electronics level as to why it works. Um, but I want to kind of talk about like this wasn't we didn't just pick this out of thin air, right? There's a really good logical reason for it. And that logical reason is something called Boolean algebra. Okay, so let me go back to the iPad, and so we'll sort of talk. Um, oops, let me go to, there we go. Boolean algebra, which is related to logic, which is related to set theory. Okay, so some of this you guys are going to see if you ever take Math 108 or do like math majory kind of stuff. Um, and for those of you who are interested in the CS major or minor, you have to do, in addition to some CS courses, Math 108, which is discrete math, or Math 219, which is combinatorics. Okay, and either path you go, you're going to end up doing some set theory and logic, but Boolean algebra is kind of related to it. Okay, so what I want to do is define um, a sort of system of writing, okay? And there's really three systems, but they're all kind of related together, all right? And so if I have, let's say, um, well, let's start with, say, a Venn diagram, okay? So this would be kind of a set theory thing. And let's say that I have two sets, A and B, okay? Then what is A and B in terms of the uh, yeah, it'd be the overlap. Okay. So let me copy and paste. This is the magic of teaching with an iPad. Well, bam, right? Isn't that sweet? All right. So what would A and B be? It'd be the stuff in the middle. Okay. And we called this the intersection. And its set theory symbol is an upside down U that goes in between it. Okay. Um, then if I talk about, well, what about if I did instead, I said A or B, or sometimes called the union. What would I highlight here? Everything that's inside either circle. Okay, and the Venn diagrams you guys probably saw in some way, shape, or form in K through 12 education, right? Now, did you ever call this union an intersection when you were in school? Maybe. The union in particular, you guys probably saw in math classes when you were talking about like intervals that a function had some property or whatever. It's sort of a way to glue two things together. Um, and the intersection is just that thing flipped upside down. Okay. Um, and then on the subject, if I have, say, for example, pick a different color here. How about blue? Okay. If I have not A or the complement of A, sometimes it's called written with a bar over it. Just sort of depends on what style notation. Okay, what is that going to be? Yeah, it's everything outside of A's circle, which includes some of the stuff that's in B, but not all of it because it doesn't include that the sliver that happens also to be an A. Okay. All right. So I can have not A, and similarly I could have not B. I won't draw it because it's the same idea. Okay. And I put this big box around it basically just so I didn't have to color the whole rest of the page. Okay. Um, right. So we have these concepts of union, which is kind of equivalent to logical or, right? Because you could say for this, what have I highlighted? The stuff that's in A or B, okay? And what have I highlighted in the and case? The stuff that's in both of them, it is in A and B, okay? And then for the blue stuff, I did not A in this case, just for sake of example. Okay, does that make sense? Okay, so that's sort of the motivation for this. And you can think about A and B as being sets that contain things, okay, which you uh, make sense in some contexts. Or for our purposes, we can think of A and B as being things that are either true or false. And that makes sense because we're wiring up circuits, and so we're thinking of voltages and all of that business. Okay? All right, so Boolean algebra is another way of writing this. And what the way we'll do this is we'll say our union, okay, which is logically or, we'll write as A plus B. And our intersection, which is logical and, we'll write with the product just juxtaposing the two things next to each other. Okay, so it looks like it's multiplication. Yes? Okay, so that's maybe you haven't seen this sort of way of writing before. It's fine. New. Okay. So let me write here English. Let's write Boolean, and let's write logic, and let's write sets. And we'll translate all of these into the other notation schemes, some of which you may have seen before. Okay, so logic would be A or B, and A and B. Sets would be A union B and A intersect B. Okay, so do you see sort of the pattern here? Um, Depending on the context, like which book you look in or what you're dealing with, you might see things written in any of these ways. Okay, we have the English words. Okay, that's fine. We've got the Boolean algebra way of writing it, where plus stands for or and multiplication stands for and. We've got the logical writing, where instead of the U's, we use V's. Okay. Um, and then for the set theory, we use the other ones. Okay. Now, you might ask, why do we have basically four different notation schemes for the same damn thing? Well, one of them is a context thing. If I'm talking about sets, I use one. If I'm talking about logic, I use the logic one or the Boolean one. And it's just sort of, I don't know which side of the bed I got up on that morning. Uh, or that, yeah, something like that. Okay. And then what's the last thing that we need? What's the symbol for not? Okay, well, in English, that's easy, right? In Boolean algebra, we'll just put a bar over it. In logic, we put a little thing in front of it that's like a minus sign, but it's got a little hook at the bottom. Okay, and in set theory, we also put a bar over it. Or in some books, you'll see a little C as a superscript for complement. That just depends on the book you're looking at. Okay. We won't worry too much about the set theory notation here because that's not the purpose of what we're doing. But for those of you guys who take like Math 108 or something later, you may see this notation in other contexts. Okay. Okay. So um, that's our notation scheme. Okay. And then we need to have some basic rules as to how all this stuff plays together. Okay. For example, what do you think a double negation should do? Yeah. So if I negate the negation of something, that's equivalent to just having the something, right? Okay. So in Boolean notation, we would say double negation is the same as A. In logic, we would say double negation is equivalent to A. And in set theory, we would say it the same way. That A bar bar equals A or A complement equals A. Either way. Okay. Um, and this symbol here in between on the logic side is just an arrow pointing both directions, kind of like in chemistry. That's all that is. Okay. All right. So double negation just is as if you did nothing. Okay. Does that make sense? Um, and then what about if I get something that's always true or something that's always false? Okay. So in Boolean algebra, the way that we'll notate this is times, or sorry, 0 times anything is 0. Okay. And this is why we use multiplication for this, because what would be another way to say that logically? This would be false and A. Well, does it matter what A is if you and it against something that's false? Okay. Um, on the same subject, then, what about um, what about if I add 0 to something? It's just the something, right? And now maybe you're starting to see the brilliance of Boole's notation, right? That true or something is equivalent to just the something. Okay. Or I'm sorry, I meant to write false, not true. Okay. Because what's the next thing I need to do is, well, what about if I do this with true? Okay. So what is one A? So this would be true and A is equivalent to A. And that makes sense, right? Because what's 1 times anything? Itself, right? Okay, so that kind of makes sense. Um, and then this one's maybe a little funny. What do you think this is? It's just 1, okay? And that may look weird. Um, okay, but with or, does it matter what A is? Nope. It could be true, it could be false, but what's false or true? True, and what's true or true? Still true, okay? So that's maybe the weirdest of the bunch. The rest of them, like you could have guessed these three just knowing like regular high school algebra, not having any clue that this had anything to do with logic. Yeah. Okay. And so there's a reason then that that notation sort of sticks because it, well, you can kind of manipulate it similar to how you do in high school. Okay. Now, we also have distribution laws like we do in high school. Okay. And so let's just write that down. Okay. So let's say that I had something like this in high school, right? A times the quantity B plus C. How else could you have written that in high school? AP plus AC. Like it's as if you distributed the quantity. Okay. Now let's make sense that that actually is exactly what we're doing in a logic context. This would be like saying A and B or C is equivalent to A and B or, oops, sorry, A and C. Okay, now that maybe isn't as easy to see that the two things are equivalent. Okay, but how could we check that the two things are equivalent if we're not convinced? Huh? A circuit, okay, or we could just draw a truth table, okay, which would be like a circuit without a circuit, right? Okay, so do it sort of conceptually. Foiling it, well, that's essentially what we just did, right? Uh, and the question is, are the two sides of this quote equation actually represent the same thing? Okay. All right, so let's say that we're not convinced and we want to make a truth table, okay? Now, for this one, how many possible input patterns are there for A, B, and C total? There's 8. Why 8? 2 cubed, okay. How many choices are there for A? 2. How many for B? How many for C? And they're all independent, yes? Does B's value have anything necessarily to do with A? And similarly with C, right? So this is the same question as asking you to flip 3 coins and how many different outcomes are there? There would be 8, okay? And we could write down all 8 and it would kind of suck, but we could do it, okay? So let's write down here A, B, C, and then, so we're going to make a gigantic table, okay? And then I need to do B or C, okay? And then I need to do A and that thing. Okay, so the stuff that I have to compute is to the right of this really thick bar, and the stuff that I just need to fill in all possible patterns is the stuff to the left of the thick bar. Okay, so does that make sense? So the stuff to the left would be, I just need all 8 combinations of the different values for A and B. Okay, and so let me just write down some of them. There's 4 of the 8. Okay, and let's go through those 4, and then I'll let you guys do the other 4 just kind of on your own. Yeah, okay. So does it make sense, the setup here? Yeah, okay. So B or C. If B and C are both false, what's B or C? Also false. Okay. What about the next one? B or C? True, because C is true in that one. B is true in this one, and it happens to be the case that both B and C are true in that last one. Okay, so those 4 entries would be there, and that makes sense, right? Because this is an OR, and what should you expect out of an OR? 3 yeses and 1 no. Okay, that's sort of the pattern. Okay, now we need to take that and it against A. All right, so what is A, which is here, and B or C? So what's 0 and 0? 0. Okay, next one. What's 0 and 1? And. Okay, so 0. What's 0 and 1? 0. And what's 0 and 1? So what do we get for all 4 of those? 0. Okay, now that's only half the table though. Okay, so let me pause. Questions about the entries we filled in so far on the table? What question, preguntas, and or fragens have you? Gucci? Uprada? No? All right. What about the other half of the table? Well, okay, so let me write down the pattern here. And you might have noticed that I'm writing down in a very particular order, and we'll talk about that order later. I'm using my head here. Okay, so talk amongst yourselves for a few moments and fill in the remaining entries in the table, and then we'll double check that everybody has it correct in une minute.
Good job. I can throw it back.
Okay?
So B or C, 1, 0, 0. So B and C both are false. So it's false. The rest are true because another one shows So for 100, A which is true and B or C which is false. So that's false. A which is true, B or C which is true. Yeah, that's just true. A which is true. Still
Just made the table bigger. All right, so let's come back together. Did you guys all get this? The one in the big green box. Okay? All right, excellent. Now, that's really only half of the question, though, right? Because this is the left-hand side of the expression's truth table. If I want to argue that this is equivalent to the right-hand expression, I need to do the truth table for the right-hand side also. And then how do I know if they're equivalent? They ought to have the same truth table. Okay, so similarly, I need to first get the two constituent pieces of the right-hand side, which would be A and B, and also A and C. Okay, so fill those out. Okay, and then finally we'll put the last one together, and I really should have made more space for the table. So let me see if the wizardry of my iPad will let me scoot it over a little bit. Oh, would you look at that? I just made the table bigger. Okay, so the A or B, let's just go through those real quickly. 0, 0, 0, 0, or A, I'm sorry, 0, 0, 1, 1. And then for C, we'd have 0, 0, 0, 0, 0, 1, 0, 1. Okay. And then for the OR, we'd have 0, 0, 0, 0, 0, 1, 1, 1. Okay, so I know I did that fast, but do the green and blue boxes match? That means that those two things are logically equivalent because they have the exact same truth table. Okay, so if you're not convinced, you can always set up the truth table and double check that in fact that they're really the same thing. Okay, this would be a conceptual way of what about if we wired this thing up as a big old circuit. How would we know that they're the same? So we'd wire up the left-hand circuit, we'd wire up the right-hand circuit, we'd power them both on, and what should we see? The exact same output pattern, right? That's equivalent to them having the exact same truth table. It just means we don't have to actually wire the dang thing up. Well, that's kind of nice. Or maybe a better way to say it is it means that we can figure out what behavior we should get before we wire up. And that way, when we wire it up, we already know what we should have. That assumes, of course, that you wire it perfectly, which is kind of a big assumption, as we've discovered, right? That you do screw up the wiring part of it, okay? But you at least know what it should do um, before you even get started. This also means that if you have some complicated circuit, using these rules and then some other ones that kind of go with it, and there's a few more we'll talk about in just a second, um, give you a way to, let's take algebra, right, from high school. You could write some big, horrible, complicated expression, but weren't there rules for how you could simplify it? Yeah. And similarly, we have with this distribution rule, with the absorption laws, with the double negative rule, and all of this stuff, and then De Morgan's laws, which I'll show you the next thing, ways that we can manipulate a Boolean expression to possibly turn it into a simpler looking but equivalent Boolean expression. Okay, so if we've got some complicated big Boolean expression and we can do some of this math to simplify it, well, then maybe we could wire a simpler circuit that does the same thing. And that's brilliant because simpler circuits means fewer parts, less money, fewer screw ups. Yeah, that seems like a good idea, but more math, right? Always the optimist over there. You have to do some more math. Okay, right. Okay, so the last thing I want to look at for right this instant on this is what are called De Morgan's laws. Okay, and De Morgan's laws are basically how does not play with the two operations. Okay, so let me write this in all three styles. Okay, so Boolean, logic, and sets. Okay, all right, so here's how this works in Boolean. The complement, or sorry, not of an and is equivalent to the or the nots. Logic, not A and B is equivalent to not A or not B. And in set theory, it would be the complement of A intersect B is A complement or B complement. Okay, so you can demonstrate any of these, the fact that they're true, by either drawing their truth tables or, in the case of the set theory thing, if you draw a couple of Venn diagrams and you color some stuff and you do the left hand expression and you do the right hand expression and the same stuff is colored in, they're equivalent, right? So either way you do it. Um, but let's kind of think about why this makes sense. All right, so um, who's in both this class and a math class this semester? Okay, so which math class? Calc. Okay, great. So you are in calculus and you happen also to be in computer science. Okay, what would be the opposite of that situation? Okay, so what's the opposite of you being both in calculus and in computer science? Well, you're either not in computer science or you're not in calculus. Does that make sense? Okay, so um, I don't know. I mean, I almost want to just stand up here and say it's clear, right? Okay, but well, if you really think clearly or carefully about it, they are equivalent, right? How could it be the case that you saying that you're in both classes is a lie? You have to not be in one of the classes. Maybe you're not in both, right? But at minimum, you got to be not in one of them, okay? And that's what we've got just in the three different logical schemes or notation schemes. Okay, that's one of De Morgan's laws. The other De Morgan law is how does negation play with okay, and it looks like this. All right, so let's take A plus B as a statement. Are you in calculus or computer science? Okay, you guys, for every one of you, that statement is true because you're all in this class. Okay, now some of you happen to be in calculus, and that's fine. But if I ask, are you in calculus or computer science, you would answer true. Okay, so what would be, how could that statement be false? That you're, I'm asking, are you in calculus or computer science? And you say no. What's the only way that that can be true? You're neither in computer science nor in calculus. So you're not in computer science and you're not in calculus. Okay, and what's the Boolean notation for and? Multiplication. Okay, or here's the logic way of putting it. You are not in computer science and you are not in calculus. Okay, another way, you are not in the set that contains all the students in computer science, and you are not in the set that contains all the students that are in calculus. Okay, all three ways of writing it all mean the same thing, basically. Right? How does a negation play with either and or? Okay, so the other thing I want to point out here is, do you guys sort of notice that there's a built-in symmetry here? And this is what makes this so beautiful in my mind, right? What is the not of an and? The or of the nots. What is the not of an or? The and of the nots, right? So in some sense, and or are complementary operations, okay, when negation gets involved. I said a magic word there. Complement. Why might that be relevant to the discussion? Complementary. Yeah, this explains why we laid out our CMOS stuff the way that we did. Okay, and so let's talk about how this relates to the logic or to the circuit stuff, and that we'll conclude with today. Okay, mind's blown yet? All right, buckle your seatbelts. We got 6 minutes. Yes.
I remember like one of the first classes we had, you were also talking about the or. So what happens like in Boolean,
Mm-hmm.
the second row? You said if we're both in like the same class, or we're in the same, we're in both of the classes that you listed. Wouldn't that negate it as well? So it doesn't fit the or statement.
Uh oh. Okay. If so, here I'm asking, are you in computer? So A plus B would be asking, are you in computer science or calculus? And you're asking, what about if you're in both? Okay, good question. Let's say you're in both. Is A or B true if you're in both of them? Yeah. Okay. So they both happen to be true. You are both in A and you happen to be also in computer science. Okay. So how could that statement, are you in math or computer science, be a lie if you're not in either? Bam. Right. Right. Okay. So sometimes actually the best way to decipher this is just say it in English. Right. And you'll be like, oh, wait, I just did it. Right. Right. And because you're native speakers, right, you just you just do this, but also because we have this idea of neither nor and whatnot in English. I don't know. Yeah, you answered your own question.
As long as it's both negative or not true.
Right.
Okay.
Okay. So maybe that's another way that I like to think about this is if I have a statement, I say, okay, under what statement is this a lie, or conditions is that a lie? Well, then think about it, right? How would that be a lie? And then, well, there you go. So what's the opposite of something being true? It being a lie, right? So I imagine people here being A and B, and are they lying or telling the truth? It's kind of like, how many of you guys have seen Labyrinth? You know, the David Bowie movie where he has like he's wearing the tights and he has like a like way exaggerated package because he's like stuffed all kinds of stuff in there. No, no. Well, okay. So there's a scene where there's two door knockers. There's a red door and there's a blue door, and uh, one of the two door knockers always tells the truth, and the other door knocker always lies. But you don't know which one's which. So you have to come up with a question, and you can only ask one question that has a yes or no answer. And you can ask either door knocker, but only one of the two, and so that you can figure out which door leads to safety and which door leads to certain death. Ooh, boom, 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 boom. No, go watch it. It's funny.
So you asked which way was the other door facing.
Yeah, that's. Don't spoil it.
I haven't seen it.
Well, don't you just spoiled it though. Yeah. So anyway, um,
I randomly watched
okay.
Boolean.
So let's take here. Let's when we do a CMOS circuit. Okay, let's take the CMOS NAND. Okay, that we wired up. How did I know that it needed to be arranged that way? Let me start with the NMOS side of it. If I can figure out the NMOS, then the PMOS is sort of forced, and vice versa. Okay, so the NMOS side, what happens when we put when we did two transistors in series? We had this. Okay, what was that circuit when we did this with the BJTs? This was an AND gate. Okay, and we could have done the exact same circuit with the NMOSs, um, but we didn't. Okay. Now, in the case of the BJTs, we had to have a resistor here in order to keep, so we didn't have a short circuit, basically. Okay. What was the trick with the AND gate to turn it into a NAND gate? We took the output and the resistor part and we put them above instead of below, meaning before the things relative to ground instead of after them relative to ground. Okay. And so what we did was we had that. Okay. So this was our NAND. Okay. Okay. NAND stands for not and. Yes? Okay. So this circuit outputs not A and B, or equivalently, A bar or AB bar, not AB. Okay. I need to do the equivalent PMOS part. Well, let's take AB bar. Okay. So this is the NMOS part. And I need to come up with the equivalent PMOS way of writing it. Well, what is De Morgan's law say that AB bar is? So that would be A bar or B bar. Okay. Well, PMOSs are the opposite of NMOSs, right? So if I have A with an NMOS, that's equivalent to having A bar with a PMOS. And similarly for B bar. And De Morgan's laws said that these should be an OR. Well, what in a circuit world is equivalent to OR? Wiring in parallel. So this is exactly why we put the PMOSs in parallel and the NMOSs in series. Just De Morgan's laws. Yeah? Okay. So we got one little thing to polish off with this, which we'll do first thing Friday, and then we'll get to some other stuff. So were you guys all able to get the NMOS, or sorry, the NAND gate working correctly? Okay, good, because that's the first step in a long process.